So the Continental America Telescopic Eclipse Experiment. I think I got that out. That's CATE, and it's casually known as Citizen CATE, just because of its fun connection with citizen scientists. This is going to be a problem. So yes, I had to take the place of Matt Penn. Padma Yanamandra Fisher is the PI on the two groups who did polarimetry, and Adriana Mitchell is our undergraduate student who actually did a lot of the programming for CATE and a lot of the work for us, and I'm using materials that they've provided, as well as the, so I'm going to talk about the experiment, why you would want to go to an eclipse to try to observe it, what kind of science you might want to try to get out of those observations, a design for a system that would accomplish those scientific objectives, a discussion of how we made it work, the citizen science aspect of the program, preliminary results, very preliminary. I'll talk about the polarimetric systems and then discuss where do we go from here if you have 70 identical telescopes and you want to try to do some science with them. The scientist who shall not be named is the charismatic leader of CATE who came up, this is Matt Penn, came up with the idea of doing the experiment, what equipment might be needed, how it would be assembled, and then how to get money to support it, which was a huge deal, and then finally working with all of the various partners to be able to pull it off. The program wouldn't have happened without Celestron, who provided all of the telescope mounts for the systems. Daystar Filters provided all of the telescopes. ColorMaker is for kind of industrial color paints and so forth. They were just interested. They provided money that helped purchase the cameras. MathWorks, those are the MATLAB people, coded all the software and have worked really hard in analyzing the sort of the metadata from all of the observations. NASA sent 2 Eclipse expeditions out in 2015, 2016, and then helped fund CATE in general. NSF stepped in at the end with enough money to buy the last dozen or so systems that we needed. This is what NASA can see of the corona on any given day. At a total solar eclipse, you kind of want to fill in what's in between. There are other systems that can do that. HAO's K-Core can, but K-Core is looking through a sky that's 1,000 times brighter than what we see in an eclipse. So maybe not as good a signal to noise or spatial resolution as what you can get at a total solar eclipse. So yes, you want to go observe one, but in order to get funding, you sort of have to have a reason to do it. And here, of course, is why we want to do this. We want to understand the on-ramp onto the expressway, which is the solar wind. This is a slide that Matt presented to congressional subcommittee to explain to Congress members what we want to do, but we really want to know acceleration of the solar wind. Here's a paper from 3 years ago, Poletto, that shows outward velocity versus height in the corona, log height. And it looks to me like pretty much of a lost lunch diagram. And the hope is that with high temporal resolution, high spatial resolution observations in an eclipse, we could nail down this better for particular coronal features. The area over which a CATE system can observe is this dotted box. So out to almost a solar radius or so, and then being able to sample an outward velocity in this range from its temporal cadence. Another thing we want to try to do is add our 2 cents to what heating mechanism is supported by these observations. Are there nanoflares? Are there alphane waves? So we want to look for bulk motions in the corona. And one of the nice things about white light observations is you're actually seeing material move, as opposed to, say, temperature changes that might masquerade what you're looking at. In 1999, on an eclipse expedition, Steve was there. We did about 4 minutes of observations of the corona at pretty high temporal resolution, pretty high signal to noise, pretty high spatial resolution, and we thought we could see some things move. But 4 minutes was not nearly long enough. So we know that we need to observe for longer than 4 minutes. So how do you do that? Well, you set up telescopes all the way across the country. And these are coded by private parties, universities, schools, parks. So you can then get up to 90 minutes of observations. What hardware do you need? What software do you need? What procedures do you have to follow in order to successfully observe the sun at the resolutions, time cadences, and so forth that are required? So in 2015, we sent a team to the Faroe Islands to observe the eclipse there. It's kind of fun to look at the polar angle of the equatorial mount here, where they happen to be observing. So the pole is up here. We used commercial software. We used what we thought was a pretty good guess for a camera, a Daystar telescope that they were using for H-alpha observations. And we got an image that looked like this. So what we learned was we have to do a lot better at understanding how to focus systems. We really needed to make that automated. We had to make better use of our observing time in order to achieve a higher signal-to-noise ratio by getting a higher duty cycle of when the shutter was actually open versus clock time. We learned that this camera sucked because it was unflat fieldable. It had nonlinear artifacts in the data. We learned that whoever was operating it had to have a step-by-step, easy-to-follow procedure that went through the calibrations and the observations in a way that you have little chance for making errors. So in the next year, we worked really hard to get the right telescopes. I characterized cameras here in Boulder, settled on what we thought would do a really good job. The MATLAB people did a fantastic job building a really user-friendly interface where you just click from tab to tab to go from setup to calibration to focus to eclipse to quick look to saving your data. And we sent 4 teams to Indonesia under NASA funding in 2016. Southern Illinois University, University of Wyoming, Western Kentucky University, and South Carolina State University sent teams. This is Wyoming and Southern Illinois. And we got an image that looked like this. This is edge enhanced. So we had the camera figured out. We had it figured out how to focus. We had the duty cycle figured out. So we had a system that was optimized for doing the solar eclipse science. Telescope's pretty simple. It's kind of close to what HAO deployed on some of your systems. It's an 80 millimeter aperture extra low dispersion element achromat. The camera itself was more than half of the cost of the entire system. And we needed to do that in order to really get our high quality images. We strobed the camera with an Arduino-based microprocessor. The Arduino did 2 functions. We had a GPS shield in there, so we had absolute time reference. And then it was able to strobe the camera. I don't know, there aren't too many old geezers in there, but in the old days, with your single lens reflex camera, you'd hook a bulb onto your camera and you'd squeeze it to take an exposure and release it, and then advance to the next one and squeeze it to take an exposure and release it. And this camera has a bulb mode. It's a TTL signal. And by doing this, we didn't have to send it software commands between exposures. We just send the TTL signal. It would take the signal, take the image, read it out, and we achieved almost a unity shutter open time efficiency of taking exposures during the eclipse. Hook it all together with a cheap PC, but you equip the cheap PC with a lot of memory and a pretty good size solid state disk drive, USB 3, and then you're able to stream those data to the computer. You say, 80 millimeter aperture? It's a big deal, you know, why 80 millimeters? Well, in Spec 1 for the Daniel K. Inouye Solar Telescope, Matt Penn introduced a concept that he called the coronal aperture of a telescope. So if you have a big telescope in a bright sky, it's effectively not as big. If you have a little telescope in a dark sky, it's effectively bigger. So if you normalize the Daniel K. Inouye Solar Telescope to 4 meters, then if you have an 80 centimeter telescope with a sky that's 25,000 times better at an eclipse versus what we expect for the DKI Solar Telescope, then it's effectively 1.25 meters. So no, it's not a 4 meter telescope, but in terms of coronal aperture, we can do pretty well. I'll go off on a little tangent here just for fun. K-core is about 1/3 meter, using 2 times 10 to the minus 6 for a scattered light. And Cosmo is 5.5 meters. That's due to the better scattered light that you'll get with a refractor on Mauna Loa versus a reflector on Haleakala. But yeah, the point here is that, yes, we have a pretty good system for observing the eclipse. So we have the system we want, we have the software to control it. Now you're going to set up a whole bunch of them across the country, but you need teams of people in order to operate these systems. So every state had a coordinator, and the coordinators in the states had training programs and practice sessions. At the training programs, they gave out the systems to each of the teams that were under their purview, and then conducted a 2-day-long training session where they learned all about how to assemble it. They built up their own systems. They downloaded the software they needed. Then they went through solar observations using a solar filter on the telescope, going through all of the eclipse observations, and then we looked at the results. Then after this, we had a series of training sessions throughout the late spring and summer where each of the teams would do something like, on the same day, we'd all go out and observe the sun, and then send our results to Tucson. And our student, Adriana, would look at how well focused it was, how their camera orientation was, how they had set up their test exposures and so forth, and then provide feedback to the state coordinators, who then talked to each of their team members about what they needed to do. And some of them had downloaded the wrong software, and some of them had their cameras funny. But as we went through the testing, we could see that we were getting better and better and better in terms of performance from the sites. Everybody had to go, including me and my partner, Dr. Richard Kautz, who was formerly of NIST. But we learned how to run one of these systems and how to operate the software, just like everybody else. It was a pretty amazing day in Laramie, Wyoming, where there was a blizzard the day before and then gorgeous sunshine the day of our practice, and melted off and got a chance to do our working. The volunteers, 27 universities, from all the way along the eclipse path. A few of them, is University of Arizona in there? No. There's a high school over here in Tucson that actually went to Idaho. 22 high schools, some libraries, informal science and education organizations, some people from national labs, And then there were, I think, 8 sites of private individuals who bought their own systems, but they went through the same training as everybody else did. I'm doing okay. I'll go on a little tangent here. The Teton High School. We realized early on that this was not a project for friends of Matt Penn. I was one of the first volunteers, and he asked me to, would I do a system? I said yes, as long as it's in Tetonia, Idaho, because that's where I'm going to be. And we got more and more universities and high schools and so forth involved. And so I called around the Teton Valley and got connected with Tom Vanderhorst, who was the advisor for the astronomy club at the Teton High School in Driggs, Idaho. And on the phone, he said, yeah, I'm interested in observing the eclipse. And so I was up there exactly a year in advance, and talked to him in person. And he had some really good ideas. He was saying, well, our students are going to learn all about the eclipse. There's no reason why they can't go over to the middle school on our same campus here and give classes to middle school students at the same time. And so I decided, okay, this guy knows what he's doing. And I just gave him my system with the approval of the project. So actually at that point, I was out in the cold. But Tom and a couple of his team members from their ugly site, this is his backyard, really took the ball and ran with it. We actually I actually learned some techniques from them. So Eclipse Day comes about. How did we do? Here's a graph of universal time and longitude. So you start at 125 degrees longitude and go across the country to South Carolina at about 40 or 80 or so. And the horizontal lines are when each of the systems had their totality program activated. So this is when they would have been taking totality images. Some of them started a little early, some of them ran a little late. In terms of when the software was turned on, they might have had their solar filter on top of it. But you can see that there are only a couple of gaps in there where we really didn't have observations running. Here's another way to look at that. We took a ramp of exposures from short to long, and that's encoded in dark blue to yellow. Dark blue means 0 exposure time. They weren't running. So if all of these teams started supposedly at the same time relative to the eclipse and then ran, what were they looking at? And you just see ramps of increasing exposure times during the course of the eclipse. You see a couple of places where they didn't observe at all. That's where it was so cloudy they didn't even try. A couple of places it was kind of cloudy and they did try. But you can see that we did pretty well in terms of coverage. There are a few places where they had glitches in their timing, and that shows in those ramps getting out of phase, but the data are still there. So several of these are going to take some hand massaging to pull out, okay, exactly what exposure was going on at what time. But that's pretty good. So 66 of 72 sites collected coronal data. 83 of possible 93 minutes of totality were covered. So weather was really good across the country. So we have our data. What do we have? Well, for absolute calibration, we have a solar filter in front of the telescope looking at the solar disk. And I calibrated some of those solar filters versus the HAO standard opal set, which was calibrated by some guy back in the 1960s. And then we intercalibrated all of those solar filters. We had to have darks to go with your solar disk measurements. You need to have flat field measurements. So we actually swung the telescope over here and looked at the sky. Took data there. Got to have darks to go with those. We did drift scans. We just turned it off and watched where the sun went across the field of view. And then we also ran for a period of time tracking. and from that we could back out what the orientation of the camera was and what the error of the polar alignment was for each of the systems. And if you look at a plot of how close they were to exactly the right camera orientation we want, most of them were right on the money, and there were a few of them that were just completely out of whack. Okay. And then we had totality data. So here's what our totality data looked like with the step of exposures. So the object was to make sure we had appropriately exposed images for each of the heights in the corona. And if you look at the stepping here, you can see that for the shortest exposures, we can see the prominences. Then you see the inner corona. And then for successively longer exposures, you step farther and farther out in the corona. So we collect pretty high signal to noise data all the way out. So once you have those data, we need to create our flat fields from our data we took on the day of the eclipse. Dark correct every exposure, apply the gain correction to every exposure, and then take each of those sequence of steps and create a high dynamic range image from each of those set of steps. So from each site, we had about 50 of those high dynamic range images. But things are going on during the eclipse. The moon's moving across the sky, the tracking's doing various things. So how on earth do you register those 50 high dynamic range images? You can use different techniques, but the one that our student who's doing the calibration found worked the best for a single site was to use a commercial package called AutoStackert, and he identifies a couple of points in the field of view, such as the top of the prominences, and then locks onto those and is able to register image after image. First step he had was just to center the moon, and then you're close, and then gets much closer with that. And in fact, I did this, and I used a very similar technique to what he's derived to register that image. So yeah, that's how he did it. So once you register images, you can create all kinds of products. Here's one with a normalized radial gradiated filter applied, which tries to make the total intensity at any given height the same, so that you see structures all the way out across your field of view. So now we have registered HDR images for each site once they're calibrated. And we have those all the way across the country. Then you've got to register those. So we have to correct for camera rotations, polar alignments. So we have that from our drift scans and also some metadata. And then how do you register site to site? Well, Logan at the University of Wyoming thinks he can use the prominences. Some of us think that maybe that'll get you close, but we might have to do, say, FFT-based cross correlations of features in the corona, but they might be changing too. Another one might be to use the normalized radially gradiated images and balance those to get centering. So who knows? But in the next few weeks, we'll find out what works for the site-to-site calibrations. Then once we have our data set of all of these registered high dynamic range images, then we can then look back and say, do we see things moving out in polar blooms and coronal structures? Do we see oscillations? Do we see whatever coming together in the corona? And that's going to be exciting, probably after a year from totality. So 28,000 exposures to create 2,600 high dynamic range images, and then we're going to blend those all together in order to try to do our analysis. Okay, so I'm done. That's where we've gotten to.
All right.
You can sit back down.
All right. Well, I was going to say thanks for your talk, David, and we'll open for questions maybe in a second or so. But
you can sit back down.
okay. All right. I will sit back down.
I'm really poor at humor. What can we learn if we look at one high dynamic range image from each of 46 sites? These HDR images were created within minutes of the eclipse using a quick look routine. So they are not calibrated, and they're only 1/50th of the data. So Matt Penn put together this animation. So on the left is radially gradiated adjusted image. On the right is a Sobel filter edge enhanced image. And I can't see much there. Let's just look at the Sobel filtered image. I can begin to see outflows down here and maybe something going on over here. But Matt went further. Let's zoom in on that one in the southeast. And 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. I definitely see things going out in that image. So the thought is with 7 times better signal to noise and calibrated, so for example, these rings are going to go away once they disappear in calibrated data. We should be able to see a lot more in a lot different places. Here's an interesting feature. 1, 2, 3, 4, 1, 2, 3, 4. If anybody can explain to me what's going on there, that would be great. We have a paper in hand. You think it's twisting or untwisting? Yeah. So we're looking at 1.7 arc seconds per pixel, and you can kind of see the pixelization there. So.
You see that with mass ejections, that kind of deflection.
Okay. Well, we didn't have a CME, but we were seeing this kind of stuff. So I'm really anxious to see what this looks like with high signal to noise. So those are the two things we were looking for, outflows and various kinds of motions to see if we can see what they are. And of course, this is just 4 of the images. So we'll have 60 of them that we can use. Kind of serendipity. We're motions and prominences, but we're observing the corona at the same time. So I think I can see, especially down on this one, a little bit of change in the corona as this eruptive event goes through. So what is going on in the corona around this much cooler material that's actually moving around? And again, with high signal to noise, that could be very interesting just to see what we see there. Okay, that's our data. This doesn't have anything to do with Kate, but this, by the way, is the corona taken from Rodeo, New Mexico last week, all the way across the sky. So, yeah, here's the zodiacal light, right here. Because that's the zodiac, yeah. Here's Jupiter, Saturn's right here, Mars is right there. Okay, so now I'm ready for questions, but I want to ask on just the Kate part. But I would like to ask a question of people here. I saw some nods when I talked about outflows, and it'd be nice to know what the acceleration is. Maybe that could tell us something about where heat is being deposited in the corona in order to cause that acceleration. Is that BS, or is that something people really would like to know?
That's a good question. I mean, it's a good question to ask. Is it thermally driven, or is there some relative force of waves or something? How do I know? There must be some waves, because the fast solar wind exists over coronal holes where the temperature is lower, so it's not consistent with the thermal change.
So Gene Parker isn't exactly right then, right?
Oh, no. But Gene got the right. Yeah, I mean, it's a magnetofluid, so you've got gas pressure. You've also got Lorentz forces, part of which is the pressure. Depending on the configuration of the magnetic field and the frequency at which it happens and the like, generate accelerations. So I just think it's a very good question.
Mm-hmm. Okay, but it would be nice to know what the.
Well, one of the things you can check is it going far? Is it way supersonic? If it is, then it's probably not pressure-driven outflow. So if you've got a minimum speed projected on the plane of the sky of this thing, if that's 300 kilometers a second, then it's above the sound speed in the corona. So you've probably got some momentum.
Okay.
That's the kind of thing you can say.
All right, that's useful. Motions? Are they waves? Waves? Okay, Mr. Wave. All right. So
Did you get any polarimetry data?
that's what I'll talk about after we answer some questions on just the intensity.
All right. So in that case, we'll actually open the floor to questions this time.
I'm
Before we commence with questions, though, I know that some of you may consider David a traitor to HAO because he went to NSO. So I implore you to keep the discussion civil. Thank you.
No, it's not done yet.
Yeah, no, not yet, but he wants to have
Okay.
a session on questions
If
about the
we're-
intensity.
If we're
Okay,
happy
yeah,
with,
there, Paul.
What do you gain from doing this different exposure time rather than just stacking short exposures?
it's a lot easier to flat field when you've got a lot of photons at the intensities that you're looking for. Yes, you might take many, many, many more shorter exposures, and I've done that. I'll show you a picture of Orion Nebula that I took using 1,000 exposures. But it's a lot easier if you're kind of always working sort of in the same range. You try to make sure your system is as linear as possible. You've got the best darks, you've got the best gains, but still, that's right. From someone who's gotten dirty there, it's a nice way to go. Yes.
You talked about some alignment tricks. You don't happen to have a couple background stars, do you?
That would be nice. And I don't think we have any. The brightest stars were a little out of our field of view. So I haven't detected any.
What is your
It's not big. It's sort of like 1.8 diameters by 1.5, something like that. Yes.
333. No, I have 3 thoughts in my head.
Uh-oh.
No, I'm intrigued. Just to make a comment, I'm struck by the fact that when you look for activity in the corona, you look away from active regions. I mean, you found things changing in the corona, so the most active part of the corona is away from active regions in these images.
No, those were just particular features that identified outflows and this beautiful twisting event. So just to demonstrate, but I suspect overactive regions we're going to see a lot.
I'm just being a bit facetious. Most people think the quiet sun does this very much.
Mhm.
You're looking at those really with quite a lot of dynamics. And the other thing, the other couple of questions. One is, how do you do total alignment, and how active you have to be with these?
The schemes were to do drift tests, and I don't know whether there's an absolute requirement of how close we needed to get, but within a couple of degrees was enough so that we didn't have any issues with our images.
You could just cite Polaris as well.
Yeah, but we typically did better than that.
Okay.
Mhm.
And then, seeing. What do you know about seeing?
Seeing sucks during an eclipse because the atmosphere is going through all kinds of stress, but I have nothing quantitative.
Do you have a feeling for it? I mean, do you see changes across the? Have you thought about it just once?
No, I haven't looked at any changes. Say,
Do you think it would be worth to try and get a really sharp focus for regulars
Mm-hmm.
and just take some rapid
That would be, yeah.
during the eclipse. And I thought that might have been useful. I don't know if you know any data like that. But, I mean, canonically, it's supposed to be what, 3 arcseconds or something? I mean, it looks better than
Yeah.
that to me from where it got there.
I'd be happy if we could say 3.
Yeah. I don't know whether it's worth doing something like this. Like
Yep.
really bright stars, something we know how to keep in focus.
Mhm.
Anyway, that's it.
Okay. All right. Polarimetry.
Carry on.
Padma Yanamandra Fisher from SSI here in Boulder thought to herself, I'd like to do polarimetry in an eclipse. And she looked through the literature and came up with my name, contacted me, would you be interested? Yes. Do you know how you would do it? Absolutely. And so Padma wrote a pretty good proposal to NASA to get funding to purchase 2 more Kate systems with polarimeters, and then to support us to program those systems, collect calibration data, go to the eclipse, collect the data there, and calibrate it. So 1 system in Teutonia, Idaho, 1 in Carbondale, Illinois. Padma and Adriana were in Carbondale, and Dick Couts and me were in Teutonia. So I had to suffer through the eclipse at this location, at the home of a friend with some other friends there, and fresh made apple pie, and well, anyway. Adriana gave a talk, actually, at NASA Media Day here in Boulder, where she explained a classical oscillator approach to why we see polarized light from the K corona. Light comes out from the solar disk, excites electrons. They then re-radiate in the direction of their oscillation, and that's what we see. So we wind up with polarized light from the K corona. The amount of polarization, the fractional polarization, varies depending on the illumination from the disk of the sun. If you're really close, you get a lot of different angles and you don't get as clean a polarization signal. If you're way out at infinity, it's 100% polarized. So supposedly the K corona is more polarized down low and less polarized up high. This is also a slide from Adriana. Here's a Kate system. Here's the Daystar polarimeter that I worked with Daystar filters to design and fabricate. And Adriana with her telescope that she really liked. She made this her Facebook page too. It was great to have a sophomore in college who could program the Arduino, program the MATLAB, analyze the data from the various sites, run a site. It was terrific. So for our system, we just plugged in a polarimeter in the optical path, controlled it from the PC, and we did time multiplexed polarimetry. We took 4 successive images in 4 different states of polarization states of the modulator. You combine those in order to get intensity, polarization this way minus that way, and this way minus that way. You could combine all the images and get intensity. You can do edge-enhanced treatment, solvable filtering of the intensity data. You can get polarization brightness out, only from the K corona. You can take the ratio of polarization brightness to intensity. But the fractional polarization is supposed to be a function of height and decreasing or increasing as you go out. So why isn't this just kind of a bright thing that's not so bright at the beginning in the inside and gets brighter as you go out? Why do we see structures here? And for years and years, I didn't think to ask that question, but I guess folks like Joan knew to, that this intensity is a sum of K corona and F corona. So the denominator gets mangled by a background. So if I knew what the F corona was and subtracted it off of the denominator, I should be able to get an image that just shows percent polarization decreasing or increasing as you go out. And for that matter, maybe we could do a least squares fit trying to optimize for zero structure at each height in the corona. So you get a constant value at each height, and then that would give you the F corona and the K corona and separate them that way. No models. That's a challenge.
Yeah, you have to have really good calibration. So just
Yeah.
facts and thoughts.
Yeah.
Can I ask a question about this, please?
No, we got a question in the back. Kevin?
Polarization decreases with, not with radial distance, but with the higher perspective of the rim. So the structures behind or in front, it will appear at a lower radial distance, but will be at a greater distance.
Ooh, yeah, that would screw all that up, wouldn't it?
So it's kind of,
Yeah, Kevin, you come up with such good ideas that blow things out of the water. Okay, yes, Phil?
Well, on the other hand, there is a contribution to the light that's dominated by something close to the top of the sky, no matter what structure. You tend to get a contribution to it. I mean, if you've got something straight out coming towards you from the middle of the sun, you don't see anything. So it means that that's probably bad, but it's not bad. It's not inconceivable to do it.
Okay,
I noticed that.
so we'll still try it, right?
Is that,
No, still somebody with lots of time will still try it, right?
Yeah, the vertical light is not supposed to change very much, so you actually know. You could use a model and go that way.
Mhm,
So that
yeah.
I noticed, is that an artifact or is that dark prominence?
Yeah, this is another interesting thing I hadn't noticed before. Prominences aren't polarized at all in white light.
There are other prominences further up on the east side that don't show up in polarized brightness over eye.
Well, this is the guy where you see a bunch of it when you're integrating over the entire course of the eclipse. So,
There were several prominences there, but I don't see one.
yeah. So there's one right in here,
Yeah.
and one down in here. But when we're taking data over the entire eclipse, we kind of wash out all of that which has been eclipsed at some time.
So my question was going to be, are all prominences the same? That you're saying wait and see because you don't see that the wash out.
I think from our accuracy, this is 0. And continuum. Now, if we were to zero in on the center of H alpha, probably it would still be 0 in our measurements, but a little bit above that. Okay, here's a fun way to look at polarized corona. This is a polarization brightness image, but it's colored by the angle of the linear polarization. So red is this way, and magenta and blue and cyan, green, yellow, and back to red again. So we proved that Adriana's cartoon was right, and this is the way the corona is polarized. But it's kind of fun to show it in this color wheel.
That includes anything? No, there's no contribution from the dust corona.
From polarization, yeah, at low heights. Yeah. Juliana here at HAO looked at PolarCam data from HAO's Eclipse expedition, K-core data, and our polarization data. This is one polarization signal of ours, so our signal of noise over the entire eclipse would be a little bit better. But they sort of look like, as a function of azimuth at a given height, we're seeing the same corona. These are not cotemporal, and some effort has been done to register these, but we can't guarantee that we're not all on the same solar center. But I'm pretty impressed at how the three instruments agree in polarization brightness. So we showed coronal polarization can be measured with a pretty modest equipment, and analysis is still in progress. what next for Kate and Kate Pole? 2024. We're all getting excited, if we're still alive by then, to go to the eclipse that goes across the country. Weather is not going to be as good as the last eclipse. It's not going across the dry western part of the United States. So I'm kind of looking at Torreon, Mexico myself. We'll see. But that's something that we could send teams to along the eclipse path. These telescopes, if the sun would ever have some activity, are pretty good at seeing sunspots and so forth. So this is taken with one of the Kate systems. Here's a poorly registered appearance of Arcturus from behind the moon. And this is just 3 frames out of a sequence. And with star systems with high time cadence, you can begin to see interesting things like multi-star systems where different components of the multi-star system would appear at different times during the occultation. So maybe some opportunities here. Went out one night and pointed the telescope at HD 209-458 at a time when there just happened to be an exoplanet transit. And I would say that, yeah, we probably saw it. So that really blows me away. 80 millimeter aperture telescope. And you just collect lots and lots and lots of photons. This was one of the first that was ever discovered. It's a big one, yeah. An asteroid occultation. This occurred over Texas, and one of the teams went out and could see the asteroid pass in front of this star. From multiple sites, you can see shapes of asteroids. You can see whether the asteroid has a moon going around it. So those could be actual pretty fun projects that would require teams going to places and maybe summer projects or whatever. 9. We figured we could maybe go another magnitude fainter. These are all images from Kate systems. I've actually measured polarization of Jupiter. The poles are polarized perpendicular to the axis of rotation. Hi, Michael. Here's that image of the Orion Nebula that was 1,000 images that I stacked. So I just took 3-second images for an hour. The moon. So we can do high cadence solar observations. Maybe American Association of Variable Star Observers could have some programs that would work for us. Near Earth objects, looking at where they are, looking at occultations. The International Occultation Timing Association actually posts events that might be of interest. That's how we discovered this one. Exoplanets, yeah, that's certainly a good teaching tool. Comets, comet tails, polarization of comet tails, linear polarimetry of whatever, planets, the moon, deep sky objects. Then we might sort of cannibalize the system, take the really nice high-speed camera with its control computer, and many of these organizations have, quarter-meter-sized telescopes, and we might do things like lunar impacts or who knows what with a higher spatial resolution. So, any ideas what you'd like to do? If you do, let me know. Because it could be fun to come up with educational projects that would help us learn something would be even better. Okay, one last round for questions. This one's for real.
Anybody? How much do you lose with the polarimeter? You lose light and you lose time cadence. What kind of impact does that have?
Well, you're collecting photons the same amount of time. So if you're just looking at pure intensity, you're only losing the transmission of the polarimeter. And the polarimeter has a linear polarizer in it. So it's 40 some odd, high 40s transmission. So that's what you lose, square root of 2 in signal to noise.
No duty cycle loss to waiting for liquid crystal.
We buried that in the read time of the camera. So the camera had a 30th of a second readout time. And so what we did is when the Arduino squeezed the bulb, it told the PC and it told the polarimeter to change state. So
How will the combined observation time of the 2024 eclipse compare to the last one?
I don't know.
It's longer eclipse.
I don't know about the total. So he's asking the total length, and I don't know. I think it's comparable. The length of time at each site is longer. It's like a 4-minute eclipse. Kevin.
So the camera can run at 30 frames a second.
Yeah. Full frame at 30 frames per second. So if you're doing something like a transit, what you want to do is zero in on a subfield, and then you can run it hundreds of frames per second.
Is the camera Arduino code accessible, David? Shareware, proprietary?
Absolutely. So, yeah, contact me about what information you'd like to know, what boards we used, and that sort of thing. And yeah, I've got different programs depending on what you're doing. So if I want to observe the polarization of Jupiter, I've got a sketch that does that. I've got another one that allows you to do adjustable exposure times, and then we've got the eclipse one.
Phil, did you have a question?
Yeah, well, it's a good question. But, we talked about any spectroscopy.
This team has not. Well, this team has, and has decided that adding a spectrograph to one of these systems is adding a device that's at least as costly as the system itself. So, adding a finder scope is a significant expense. So if we wanted to do spectroscopy, then the way to do that would be to say, here's how it would be done. Here's the spectrograph you could put on the telescope, and there's some commercial ones out there that would work pretty nicely. And then go for funding to buy 70 of these. And then you'd also have to have money in there for training on how to use them and what the project would be. So it's not completely ruled out, but it's a challenge.
I was also thinking of, I think you've got the next eclipse coming up, but your camera things could be very, very handy for some of the global stellar observing programs. So you have Tim Brown, and then you have the song.
Mm-hmm.
These are all things that are, you have half-meter class telescopes, and they're doing tons of astronomy.
Mm-hmm.
You could think of optometry if you could do very highly accurate differential optometry. I mean, but it all requires investment. But you've got a very nice, seems as if you've chosen a very nice camera. It looks like it could potentially be not true, it's just pushing it too far from the magnitude.
Mm-hmm. Yeah.
I mean, I would definitely wonder about talking to Tim Brown and whether they're going to talk to
Okay.
they could tell you it's a real way, but they might want to use it for something. Well,
Mm-hmm.
Are these 70 systems in a storage shed somewhere?
Oh no, each team got to keep theirs. That was one of the wonderful things. So, they're we're hanging out there what kind of programs we can do. So you saw the exoplanet one, you saw the various transits. Several of the teams are doing star parties for their schools and things like that with them as well. Yes?
Do the teams still collaborate?
We have bi-weekly teleconferences among all of the state coordinators. So we're working on other projects. One of the things we've learned is that finding objects at night is really, really hard. And so we have an additional Arduino-based controller for the mount that makes this bottom-of-the-line mount look like a sophisticated go-to mount. And for under $100, we can build those up. I built 2 for our 2 polarimetric systems. And so we're equipping teams with those where you go to a bright star that you can see and then say, okay, now let's offset from that and go over to HD 209 458 and make our observations. Yes?
Can you repeat the polarimeters, the polarization of light around an object? What does that mean?
Boy, howdy. How many families have been fed doing solar polarimetry? So there are lots of different ways of creating polarization. And I showed Adriana's slide of how we create polarization in the corona, and then that can be used to go back to what the electron density is in the corona. As an example, I've done some astro polarimetry as well, where if you look in the Pleiades that are illuminating gas around them, you get a similar effect to what we see in the corona. And you can get these rainbow-shaped figures around each of the bright stars in the Pleiades. So that shows that you're getting scattered light from electrons around those stars. But it goes on and on of what kind of physics you could do with the polarimetry. And there are people here, I'm sure, who could come up with some great ideas.
Which star the dust is being illuminated from?
You can by the colors, by using your rainbow. Yeah. Yep. So you can see where it's coming from. And there's some areas where you say, oh, this is kind of polarized this way, but we've got several stars out here. They're probably averaging together to get that color.
Any more questions? No? Let's thank David again.